All right, let's go review some things we talked about over the last couple of lessons. Actually, really just last lesson, we started talking about a new ordered list of numbers. In general, any ordered list of numbers class that follows a rule is called a sequence. But if the sequence is formed by multiplying something by each term to get the next term, constantly multiply by that again, multiply again, over and over again, that sequence is referred to as what, Brian?
I don't even know at this point.
Amy,
Geometric.
a geometric sequence. What is it, Brian? Geometric sequence. My own April Fool's joke. It just wait till later. Anyway, geometric sequence, as opposed to the sequence in which you're constantly adding something. Other Michael?
Recursive.
No, you. Anyone?
Arithmetic.
Arithmetic sequence. So the arithmetic sequence you're adding, the geometric sequence you're multiplying. By the way, what do we call the thing in the arithmetic sequence that constantly gets added? Now, Other Michael?
Argument.
Thing that gets added to each term to get the next term in an arithmetic sequence. Aubrey? Anyone? Common difference. The common difference is what we add. In a geometric sequence, though, we're multiplying by a constant. What do we call the thing we multiply by over and over again? Jennifer? You're the one who told me. It's your own fault. They've been called wrong names in other classes, and I'm using all their wrong names. So you're not going crazy, George, or Gavin, whatever your name is. Common ratio is what we multiply each term in a geometric sequence by to get the next term. Now with the arithmetic sequence, remember, our formula is that any term is equal to the first term plus the common difference times one less than the term we're finding. Now usually I wrote n minus 1 times d. I wrote it this way so you can see kind of a comparison. In the geometric sequence, to find any term, we're still going to start with the a sub 1, not a to the first, but a sub 1, the first term. But in a geometric sequence, we don't add class, we multiply. And it's not a common difference that we're adding, but a common ratio, or r, that we're multiplying. And we don't multiply by n minus 1 class, but rather to the n minus 1, right? We raise to the n minus 1 power. Do you see how they're similar? But the geometric sequence steps everything a level up. It does it always bigger and better, right? What's bigger and better than addition? Multiplication. What's bigger and better than multiplication? Raising to a power. It's just one step up. Just maybe seeing it this way help you see the similarity, but then also the difference between the two of them. Not the common difference, just the difference. We also said with a geometric sequence, not the case with an arithmetic sequence, you could, by having a negative common ratio, bounce back and forth between positive and negative. Again, that's not going to happen in an arithmetic sequence. You'll have positives, then you may hit negatives, but then they'll just keep staying negative. Or you may have negatives and it hits positive, but it's going to keep staying positive. Geometric can go back and forth. What's that term for the geometric sequence that goes back and forth from positive to negative, and so forth, because of a negative common ratio? Ms. Kevin? Alternating geometric sequence. That's all stuff we talked about yesterday. We practiced yesterday doing some odds and some of the evens. We're going to get some of the problems we missed yesterday. Page 472 to 473 in your textbooks. Bunch of numbers 4, 8, 12, 16, and 20. 4, 8, 12, 16, and 20. Multiples of 4. And Other Michael already finished them. 4 and 8, obviously you won't need this formula, but for 12, 16, 20 you will. Just another minute or so to be finishing up. All right, for sake of time, pencils down even if you're not finished. Let's take a look at these together. Number 4, we're going from a 256 to a 128 to a 64 to a 32. I like to find the smallest numbers in the sequence and use them to make the comparison, but essentially what are we doing here in number 4? Hey, you? Okay, practically speaking, yes. Nothing wrong with saying we divide by 2. Technically, we don't divide, class. We multiply by the reciprocal. So technically, Maddie, what are we doing? Multiplying by a half. So practically, we divide by 2. Technically, we multiply by a half. Regardless of which way you look at it, though, the next term is 16. Number 8, what are we doing here? Amy?
We are multiplying by a negative 1/9.
Good. Technically, we are multiplying by negative 1/9, and so the next term is?
9.
A positive 9. Good. You could think dividing by negative 9, but again, the technical answer is you're multiplying by negative 1/9. How many got 16 and 9 as the next numbers for each of those? Then on number 12, here's where we needed to use the formula to find that 9th term of the geometric sequence. First of all, to find the 9th term, or class, we would say a sub 9. We're going to start with the first term, which here, Jennifer, is -6. And we're going to multiply this by the common ratio. But what is the common ratio here on number 12?
2.
A positive 2, not a negative 2. There are negatives, but it's not bouncing back and forth in an alternating sequence. So we do have a positive common ratio here. And then the n-1 power would be the 8th power. So we'll raise 2 to the 8th, multiply that by the 6. Remember, raise to the power before you multiply. What is the 9th term of this geometric sequence?
Negative 1,536.
Good, negative 1,536. Number 16, we're finding the 6th term of the sequence. They actually did the first 4 numbers for us already. What's the common ratio here, Brian? 8. So we could just take the last number they gave us times 8 again. Maybe use that k, or plug it into the formula. A sub 6 equals 16 times 8 to the 5th power. Our 6th term is going to be?
524,288.
Good, 524,288. And then for number 20, finding the 7th term. Here we've got the alternating sequence. So we know the common ratio is going to be negative. And Aubrey, what is the common ratio here in number 20?
2.
On number 20? Not the first term. The first term is 2. What's the common ratio?
Negative 5.
Negative 5. We're going to end up raising that to the 6th power, multiplying. What is the 7th term?
31,250.
go to positive 31,250. How many got those last three correct? Are there any questions on any of those? Any questions on any of those? Any questions on geometric sequences? Questions on that? I do want to point something out very quickly. Look back at the first two we did, number 4 and number 8. Look at the numbers in number 4 with me. 256, 128, 64, 32. The next number we said was 16. What would be the next number, class? 8, then 4, then 2, then 1, then 1/2, 1/4. It just keeps getting smaller and smaller and smaller and smaller. Can you ever actually get to a 0? No. You can keep cutting things in half, theoretically, without ever actually getting to nothingness, okay? Same thing happened in number 8, right? Now it was alternating, it was bouncing back and forth. So you had a really big positive in 59,049, really tiny negative, negative 6,561, then a smaller positive, 729, less of a negative, negative 81, positive 9. What would be the next number? On number 8? Negative 1, negative positive a 9th, negative an 81st, and it's kind of coming, if you look, picture the number line with me here, that's what I'm picturing, like, they probably don't know what my hands are doing. Positives and negatives, so I'm picturing positive, negative, positive, negative, positive, negative, positive, negative, right around that 0 point. Does that make sense? That's what we call a convergent geometric series, or sequence rather, a convergent geometric sequence. I can't make it hard to save my life. Convergent geometric sequence approaches 0. Convergent geometric sequence approaches 0. And the reason it approaches 0 is because the common ratio is a fraction. We could say that the absolute value, okay, forget the positive, negative side of it, right? One of those was alternating, one of them wasn't, but they're approaching the 0 regardless if the absolute value is less than 1. Translation, you have a fraction, or you could say you have a little fraction, right? So if the common ratio is a little fraction, that is that its absolute value, forget the positive, negative for a minute, because that just affects whether it's alternating or not. If the common ratio is smaller than a 1, you're going to get a convergent geometric sequence. It's going to approach 0. But a lot of the sequences we've seen, some of the ones we did yesterday, for instance, you look at number 1, the very first problem, 13, 26, 52, 104. The next number on number 1 class was 208. Double that again because your common ratio 2, right? Double that again, you get 416. Double again, 832. Double again, 1664. I'm sure that was a great year. Keep going, right? You keep doubling, right? Eventually, it's going to approach class. Excuse me, on my perspective, okay, yeah, that's that I had it right. It's going to approach infinity. I'm like, my backwards, I gotta always think your number line is backwards, but it's going to approach infinity, right? Look at number 5. Not number 5, that's not what I wanted. Number 12. Number 12, we've got negative 6, negative 12, negative 24, negative 48. Genesis said the 9th term, by the way, is going to be all the way down at negative 1,536. And it just keeps getting smaller and smaller and smaller, approaching class negative infinity. They're not approaching 0 because their common ratios are not less than 1. Their common ratios are not little bitty. They're bigger than 1. So you're going to get values that just keep getting bigger and bigger and bigger, or smaller, smaller, and smaller toward positive or negative infinity. We call this a divergent sequence. A divergent geometric sequence. It goes away from the 0 point, or that central point. So we would say it approaches positive, negative infinity. Now, interestingly, it could approach positive infinity, or negative infinity, or both. Right? For instance, if we're looking at number 6, here on page 472. Notice we have a negative 4, which, okay, your perspective, negative 4, 28, negative 196, 1,372, negative 9, and it actually approaches both of them because of the alternating method. Does that make sense? So you could get either positive or negative, or both positive, negative infinity being approached by a divergent sequence. Reason for this, the absolute value of the common ratio is greater than 1, or not a little fraction. Now technically an improper fraction messes with this, For our purposes, I don't think they give us a whole lot of weird fraction or decimal-y stuff. It's usually either an integer or a proper fraction they've been giving us. But this is your divergent sequence. You got a big common ratio. So big common ratio, divergent, it goes toward the ends of the number line. Little common ratio that is a fraction, something less than 1, convergent. Flip back to page 471. There's a few ways you can spot this. One, I've already kind of pointed out to you. Just look at the numbers themselves, right? And see, what are they doing? Are they converging at 0, or are they diverging to either positive or negative infinity? Look at example 10 point, by the way, graphically, they show a couple of these. Page 470 at the bottom. They actually took the time to plot the different values. And notice how the values keep getting closer and closer and closer down to that x-axis, down to that 0 mark, right? That's convergent. And then you see the opposite at the top of page 471 where the values are growing bigger and bigger and bigger, departing away from the 0, going toward infinity. See that divergent? But look at example 10.4f. It says determine whether the geometric sequence a sub n equals 3 to the n over 4 converges or diverges. Well, there's a couple ways to approach this. One way is to do what the book shows. So I want to talk through what the book does here. They say 3/4 to the n. Well, no, it's not. It's just the 3 to the n. The 4th isn't being raised to the n. Do you see that? It's not 3/4 in parentheses to the n, just the 3 to the n. So we could write it a 4th times 3 to the n. Well, that means that the a sub 1 must be a 4th, and the 3 must be the common ratio, but instead of n minus 1, that particular sequence has just an n. The common ratio then is a 3. Is 3 bigger than 1 or smaller than 1, class? Bigger than 1. So we've got a big common ratio, so hence it is divergent. The other way is you could actually plug in some numbers. What if the n is a 1? What is the first term of that sequence, anyone? I heard it? Well, 4ths, right? Because we have the 1/4. So if this is a 1, that's a 3 times a 4th is 3/4. What if the n is 2? What's the second term? Go careful. Exponent 2, 9/4, right? If it's a 3, the third term would be 27/4. Are the numbers getting smaller and smaller towards 0 or bigger and bigger toward infinity? Bigger and bigger. Maybe decimals would help, right? 0.75, 2.25, 6.25. If we went decimals, you can see the numbers getting bigger, right? Hence divergent. Look at the next example, 10.4g. Looking at this, we've got a -16. From your perspective, -16, 8, -4, 2, -1. What's it approaching, class? 0. Now it's coming at it from both sides because it's alternating, but it's approaching 0. So clearly this is a convergent sequence. The other way we could do this is we could actually figure out the common ratio. Take any number divided by previous. What's the common ratio, class? -1/2, right? But ignore the positive or negative for a minute. -1/2 or just a half is less than 1, right? So hence a convergent sequence. So that makes sense how to spot the differences between them. Also, you just look at the list of numbers. Hey, they're getting closer to 0. Look over now at page 473. Let's kind of wrap up this idea of geometric sequences. Number 23, there on page 473. Converging or diverging? Is it converging or diverging? Well, one way we could figure it out is by actually figuring out some numbers. Another way is to figure out what's the common ratio. I think plugging in numbers is easy though. What's the first term on number 23, class? 2/5, right? 2 to the first, which is 2, over 5 is 2/5. What's the next value? What is it? 4/5. Then, third term, 8/5. Next term, 16/5. Obviously, we're just multiplying by 2, right? The common ratio is 2. So one way is figuring out the common ratio. The other way is look at the numbers. 0.4, 0.8, 1.6, 3.2. Are the numbers approaching 0 or infinity? So would this be convergent or divergent? It's divergent. It is a diverging sequence. Number 25. Again, 2 ways to approach this. One is to look at the common ratio. The other is to actually plug in some numbers. I think numbers work fine here as well. What's the first term? -3, 6, or we could say -1/2. I'm going to leave it just like this, though, for now. What about the next term? Term 2. N is 2. 9/6. Not negative though, positive, because even power. All right, again, a sub n equals negative 3 to the n 6, right? What's the next term? Negative 27 6. Next term? 81 6. And it's going to keep on going, right? But I mean, negative a half, 1 1/2, negative 4 1/2, whatever that is, 15 1/6. Is that right? No. 13 1/2? Yeah, 13 1/2. That can't be right. That'd be 91 B. Okay, do we see, is it getting closer to 0 or closer to positive, negative, infinity? In this case, both positive and negative, because notice the common ratio, the R value, the thing being raised to the power here, is a negative. So alternating, but also the absolute value is bigger than 1. So again, like the last one, it is diverging. Number 27, just looking at the numbers, converging or diverging?
Diverging.
Diverging. It's getting really big really quickly, isn't it? Now there, the common ratio is of power, isn't it? Because you go from 2 to 6, that's times 3. Then 6 to 128 is times something else. Something seems flawed with their numbers here. But anyway, look at the next one. This one is actually geometric. I'm not sure what happened to number 27. The numbers don't seem to be working. That or my brain's not working. Yeah, I don't know what they did there. Number 29, convergent or divergent? Which one? Convergent. Notice the smaller the denominator, the bigger the denominator gets, the smaller the value, right? You cut a pizza 6 ways, you get a decent sliced hunk of pizza. You cut a pizza 18 ways. You ever seen one of those pizzas where it's cut into a bazillion pieces? You get like this little sliver. And then you really want sliver, 154th. Like 2 bites, if that. And then 162nd, clearly convergent, it's getting closer to 0. Do we see the difference between the two? All right, you do the evens now, 24 to 30. 24 to 30. Again, you can either determine the common ratio, compare it to 1, or just look at it and think. Is it going to infinity divergent or 0 convergent? Doing those 4 evens, 24, 26, 28, and 30. Finished, Brian? Any finished? Other people? Not finished? Yes, finished?
Yes.
Finished. Ms. Campbell? Robert? And Jennifer's like, I am not finishing. I don't want to call my name. Too late, I just did. Hey, you was finished. All right, number 1. Converging or diverging, and how did you figure it out? Aubrey?
Diverging.
Okay, why?
Because the numbers are getting bigger.
Okay, on both sides, technically, right? It's alternating because of the negative common ratio. What is the common ratio? Negative 4. Basically, whatever's raised to the power is the value that's going to be the common ratio. So negative 4 is the common ratio. Absolute value is bigger than 1. It's going to be divergent and going to both positive and negative infinity. How about 26? What did you get for that? Hit you? Well, if you look at the formula, what's the common ratio? 1/7, right? So that's a fraction, which tells me it should be converging. This one was hard to plug into the calculator, though, because you plug into the calculator, you have to do 1/7 divided by 49, 1/49 divided by 49, 343rd divided by 49, and kind of keep going from there. When you plug that into the calculator, you're going to get really small fractional values or decimals, and they just keep getting more and more like that. 1/7 divided by 49, we get 1/343rd, which, let me change that to a decimal. That's a 0.0029. 1/49 divided by 49, 0.00041. 1/343rd divided by 49, 0.000059. I mean, you can see it basically keeps getting closer and closer to 0. So 2 ways to approach it. One is to spot the common ratio. The other is actually plugging the numbers, though this one's annoying because of the decimals you get. But convergent there. Number 28 for redemption. What'd you get? You. This one is divergent. The common ratio here is 5, and it's rapidly approaching infinity. What about number 30? What did you get, Amy?
Divergent.
Divergent common ratio here was 6, and again, rapidly approaching infinity. Anyone perfect? You got diverging, converging, diverging, diverging? All right, questions on any of those? All right, those are geometric sequences, list of numbers. Next thing in your notes, let's talk about a geometric series. We should have a pretty good idea what this is. In general, what's a series? The sum of numbers, right? So here's your definition. You could probably have predicted this. A geometric series is the sum of the terms in a geometric sequence. A geometric series is the sum of the terms, S-U-M, of the terms in a geometric sequence. The sum of the terms in a geometric sequence. That's a geometric series. Now, we're going to look at a couple of different ways to approach the geometric series. The easiest, though, is what we're going to look at first today, and that's what we call a finite geometric series. A finite geometric series. This assumes there is a predefined amount of terms or number of terms that we are going to find the sum of. Now picture this. Something that goes to infinity. A divergent sequence. If you add all the terms together, what you gonna get? Infinity. It goes to infinity. You add all those other terms that are going toward infinity. Of course they're going to add up to infinity. If it goes down toward negative infinity and you add up all the terms, what you going to get? Negative infinity. Now, the fun one is the alternating one. Because on one side it's going toward infinity, and the other side is going toward negative infinity. Do they cancel each other out? That's always the fun one. We're going to get to that. The convergent, on the other hand, it's constantly getting smaller and smaller towards 0, right? So there, it's like you're adding virtually nothing plus virtually nothing more plus virtually nothing more. It kind of gets to a point where it does stagnate to a final sum. We're going to look at that in lessons ahead. Okay, so if I'm scaring you, sorry. Back to the finite geometric series. We've got a predefined number of terms. Here's your definition. It's going to be the sum of specifically the first n terms in a sequence. So we're going to have a predefined number of terms. It's always going to be the first however many terms in the geometric sequence. Here's your formula. The book takes some time to work it out. We're kind of running low on time, so I'm just going to get straight to the formula for you. Write it here and on the formula page. We're not going to use the sigma notation. We're going to reserve the sigma, the Greek S, for arithmetic sequences that are added together in a series. We'll use capital S sub n is equal to the product of the first term times 1 minus r to the n all over 1 minus r. A sub 1 times 1 minus r to the n all over 1 minus r. Copy that down there in your notes, then go back to your formula page. This is formula 10, I believe. This should be formula number 10, and it's for a finite geometric series. A finite geometric series, formula 10. S sub n, again, we don't need a lower bound, and that's what the sigma notation is used for, lower and upper bounds. We don't have a lower bound. We're starting with the first term always. So we'll just go S sub n is equal to a sub 1, that first term, times 1 minus the common ratio to the nth power all over 1 minus the common ratio. Again, page 474 has kind of the explanation for that, but time is beginning to escape us, so we will forego the explanation. Sorry, I didn't mean to be in the way of the formula. Do turn to page 474, though. Once you've got this copied onto your formula page, let's head back to your notes, and let's look at the first example problem. At the bottom of page 474, go ahead and read that problem that's there in bold for us, if you would, Other Michael. Page 474, example 10.5a.
Find the sum of the first 7 terms of the geometric sequence where the nth term is defined by a sub n times 16 times the quantity 1/2 to the n minus 1 squared. Use the geometric sequence formula. Don't list the terms and add.
All right, so they give us the algorithm for the particular geometric sequence we would be using. 16 is the first term, and 1/2 is the common ratio. That's going to be the first key. Really, the only key to the problem is you've got to identify what's the a sub 1, what's the r. And it did specifically ask for the sum or the series class of the first 7 terms. So we're going to find s sub 7, the series of the first 7 terms. Make sense? Is equal to the first term class, 16, times 1 minus r, which is 1/2, to the nth power. Well, the nth power is the last term that I'm finding the sum of, or the series of. That's going to be the 7th power, all over 1 minus the common ratio. Do we see how we're plugging in the r, the n, and the a sub 1? N is the number that we're going up to, which is the 7th term. A sub 1 is the first term. R is the common ratio. Easy enough? On your calculator, raise 1/2 to the 7th power. Should be 1/128th if I'm not mistaken, right? Then you're going to subtract that from 1. Here's the easiest way to do it. While your calculator says 1/128th, hit the positive negative button to make it a negative, and then add a 1. And that should give you 127 128ths, correct? Okay. Normally, we won't write all this stuff out. We'll let the calculator handle it all. We're going to multiply that by 16. And that should give us, what fraction are we at now? 15 and 7/8. All of that is over 1 minus 1/2. Well, what's 1 minus 1/2? 1/2. So we're going to divide that now by 1/2. And it's going to give us 31 3/4. And there we go. So it's really, again, kind of like with the other, it's just a matter of plugging it in to the calculator accurately. And of course, they left their answer as 127/4, but whatever, I digress. Look at example 10.5b. Read that example for us if you would. Jennifer.
Find the sum of the first 6 terms of the geometric sequence 3, 6, 12, 24 without finding the remaining terms.
All right, find the sum of the first how many?
6.
6 terms. And this would be pretty easy just to figure it out without a formula, but we'll do it with the formula. We'll do S sub class 6, because we're finding the sum of the first 6 terms. I already know, by the way, this n is also going to be a 6, right? The a sub 1 should be what number, class? 3, because it's the first term. And then 1 minus, now what is the common ratio here? It's a 2. So we're going to have 2 to the 6th all over 1 minus 2. Now let's get the denominator real quick, because that's easy, right? 1 minus 2, class? Negative 1. Which basically means we're just going to change the sign of whatever we get in the top, right? 2 to the 6th. What's 1 minus 64? Negative 63. So it's really 3 times negative 63 all over a negative 1, or you could just cancel those two negatives. And we get 3 times 63. 189. Or if you multiply by the negative, negative 189, then divide out the negative 1 to get the positive 189. Questions on how to use the formula? Page 479. Page 479. Go and read number 1, if you would, please. Ms. Kendall.
6 terms divided by a7 equals 8 times 1/2 to the n minus 1.
All right, what's my formula that I use to find a geometric series, or the sum of terms here, Kendall?
S sub n equals a sub 1 times 1 minus r to n all over 1 minus r.
Let's say that together as a class very quickly, and then we'll pick back up with the problem. Class, S sub n equals a sub 1 times 1 minus r to the n all over 1 minus r. Again, S sub n equals a sub 1 times 1 minus r to the n all over 1 minus r. All right, so we plug in the values here, and we're doing, Kendall, back to you, S sub 6 is equal to 8 times 1 minus a half to the 6th power all over 1 minus 1/2. All right, at your seats. The denominator might be easiest to simplify. What's 1 minus a half, class? A half. So maybe take care of the denominator because it's easy to do. I do the half to the 6th, make it a negative, and then add 1. Multiply that by the 8. You should either have 7 and 7/8 or 7.875 in your numerator. Then we simply divide that by a half, and we end up with what for our sum? 15 3/4, or 15.75. Before I move on to the next one, does anyone need help with the calculator seeing how to plug those numbers in? Any questions? How many got it? You're good to go. You feel like you know how to enter it on the calculator.
Answer in fractions.
It's either 15 3/4 or 15.75 or 63/4. Any of those answers would suffice. Okay. All right. Number 3. What do we find in here? Amy?
First 8 terms defined by a sub n equals 12 times 6 to the n minus 1.
All right. So we'll do S sub
8.
is equal to, in the top,
12
times 1 minus
6 to the 8th.
all over.
1 minus 6.
All right. So again, the denominator is easy, class.
-5.
-5. And then I got 12 times whatever 1 minus 6 to the 8th is. And what is 1 minus 6 to the 8th? What does this value come to? Anyone?
Negative 1,679,615.
Yeah, negative 1,679,615. How many had that? And then we'll multiply that by 12 and divide away the -5. And we get an enormous number. Well, again, you have here clearly it's going to be with a common ratio of 6. You know you're going to have a divergent sequence that's approaching infinity very rapidly. And so you've got a value approaching infinity. The first 8 terms are going to add up to a very big value also. What does it add up to, Jennifer? Amy?
4,031,076.
There we go, 4,031,076. Tackle number 5 at your seats. Let's see if we can figure it out and plug in here.
What's in there? What the exact numbers we have? 14 instead of 615?
So, if you want to change it to a fraction, you just use the
You can roll with the decimals, it's fine. Alright, so. Plus 1. Oh, I got you. Okay. So, don't look at it as a negative 68. The negative isn't in parentheses with the 6 itself. It's a 68 is 1 minus whatever 68 is. So 2 ways to enter it. 1 minus 6 to the 8 equals. Though, depending on, if you have fractions, it may mess it up. So what I like to do is I have to go ahead and do the 6 to the 8. Make it negative now to do the minus, and then plus the 1. They both ways will work, right? So you could do straight up 1 minus 6 to the 8 equals. Then multiply that by the 12, and then divide that by the negative 5. Does that make sense?
Mm-hmm.
Okay. Number 5. All right, Brian, how do I write the formula with these specific numbers filled in?
x sub n, 8 equals 21 times 1 minus 11 ninths to the 8th power over 1 minus 11 ninths.
1 minus 11 ninths, lovely. What is 1 minus 11 ninths, anyone?
Negative 2 ninths.
Negative 2 ninths. Your calculator can do that for you. Or if you just think 9 ninths minus 11 ninths, negative 2 ninths. And then we've got the joys of 1 minus the 11 ninths to the 8th. And it comes out to a really weird decimal. Like negative 3.979, blah, blah, blah. Multiply that by 21 to get an equally weird number, negative 83.573, blah, blah, blah. Divide that by the negative 2 ninths. And we end up with, yep, just fact checking my answer, it is correct. We end up with what, Brandon?
Well,
Or Brian?
I didn't have a 3 at the end, so I just used the 0.57, but I had 376.065.
I should have been 376.0797. Did it tell us how to round? It didn't, so it's just kind of up to you how you rounded. Give me a few decimal places and then cut it out, just because, we're lazy. So I kind of cut it there. Questions on this one is weird. But you got a really weird common ratio, so what do you expect? It's going to be a strange number. I don't think that converts to a fraction. No, my calculator's not letting me convert that to a fraction. Questions? All right, that's if they give you the algorithm where you can see the a sub 1, you can see the r, the common ratio. Number 7, 9, and 11, they don't give us those, but we can find them pretty easily. For instance, number 7, read it real quick if you would, Aubrey.
The first 6 times defined by 10, 39.
Okay, so we're going to have s sub
6.
is equal to
10.
times 1 minus to the 6th all over,
1 minus 3.
which, yeah, the 1 minus 3, of course, class.
Meaning
Now, before we go any further, do we see how Aubrey came up with these numbers? We're all good, okay? And then we do the math. That wasn't so bad. By the way, if you wanted to fact check, this is a good one to fact check on, right? We had 10, 30, 90. What's the next number? 270. Then 810. And then the last number is, I have to switch to semicolons. And if you wanted to add those together, it wouldn't take you that long, right? 2,430 plus 810 plus 270 plus 90 plus 30 plus 10. And sure enough, there's the 3,640. So again, you wanted to check your work. That's one way to do it, especially if the numbers aren't that bad and you're not taking too many of them. Right? Not a bad idea. How about number 9? Read that one for us if you would. Hey, you. All right. So how would we set up the formula here? Well, careful. It's any number divided by previous. Okay, minus 3 to the 10th all over 1 negative 3. Which of course 1 minus 3 class? Negative 2. All right, and then comes the fun part of the 1 minus 3 to the 10th. Multiplying that by 24 to get a really big number. And answer, Brother Michael?
708,576.
Any questions on that one? I feel like we're getting the hang of how to use the formula. By the way, if we didn't want to start at 1, right? This is for the first 10 terms. What if I only wanted terms 4 through 10?
You do 1 through 3.
Find 1 through 3 and subtract it away, right? So I mean, we could do it. We could find partial, right? But we don't want to. And then number 11. How would I set up this one? Let's see. Who haven't I called in a while? Amy? I thought Amy just did one. I don't know. Amy, you've been voluntold by our High Royal Exalted Senior, and her word is law. So, Amy, how would we set up the formula for the series on number 11?
S sub 8 equals 13 times 1 minus 2 to the 8th over 1 minus 2.
Which again, denominator is just a negative 1. I guess that'd be a negative 127. Nope. Negative 255, right? 2 to the 8th, 256? Yeah. Negative, and then make it negative. Yeah, so times 13. And we're good to go. Again, you don't necessarily have to show this in between step, though it's not a problem to, but you don't have to show that in between step. Questions on this? All right, homework for this evening is to do page 479. Page 479, numbers 2 through 12, the even. We just did the odds. You're going to do the evens for homework this evening. Page 479, 2 through 12, the even. Also, on page 480, there's 3 sections on the page. The middle section is the review 10.5. Page 480, the review 10.5. It's in the middle of the page. Do the 9 through 12. Page 480, in the middle of the page, do 9 through 12. Also, we have a test coming up in lesson 156. That's on Wednesday. Test coming up, lesson 156. That's on Wednesday. Matrices, series, sequences. Not necessarily in that order. Matrices, sequences, series. Okay? And obviously, we'll look at that information more as that day approaches. But we're finishing up here tomorrow, Monday, and then reviewing Tuesday. So lesson 156, test 10 coming up. All right, have a wonderful rest of your day. And when the bell rings, well, I guess it just rang. You're dismissed.